Yeah, send me the link. I'll link to it on my website. Thanks. All right, guys, I'm gonna go ahead and get started. So last class we started to get into directing group effects. So once you have a group that's already on a benzene and you do an electrophilic aromatic substitution, there are in essence multiple positions that you can react at. So there are multiple products that you can sort of generate. And it's sort of, again, we went through this sort of naming, ortho meta para, which basically reflects whether it's on the carbon immediately next to it, sort of with the carbon in between, or sort of across one another. And what we began to get into last class was this sort of question of how you can reason any selectivity that might be involved. And so I left you guys with the basic question of, if you react in one of these alkenes, right, just through, take the alkene, treat it as a nucleophile, and imagine some of the intermediates that you might generate. Right, we thought about a few different compounds. Right, so if we reacted at this carbon from this alkene, right, we get a carbocation at this position. If we say, for example, reacted at this carbon here, we leave behind a carbocation there. Right? And if we reacted on this alkene, right, within that system there, we'd leave a carbocation here. Right? And so these would reflect the first steps of electrophilic aromatic substitution. Right? And so they're effectively intermediate resonance forms that you can imagine would be sort of first step. And as we discussed, in line with a lot of the chemistry that we've seen in the past, the reactivity is often dictated by the sort of relative stability, right, of the resulting cations that you might be able to generate. And so if you look at these molecules that you might see here, you might be able to view a couple of them as being more stable than the others, right? And so right away, if we look at this molecule that we see right here, right, it should be fairly apparent that there's a really major stabilizing effect from that carbocation, right? And that's based upon the lone pairs that we have on that methoxy, right, donating into that pi system there, right? Turns out that we can get the exact same effect here as well, right? When we have that carbocation at that position, we can imagine the resonance form. It's an allyl cation. Right, so you can imagine that same resonance form where now we put the lone pairs next to it. So we can draw it directly onto that oxygen, or however you want, but clearly there's this stabilizing effect here as well. And so both of these positions, the ortho and para positions, have this resonance stabilizing effect. In the case of a cation, right, in the case of that cation at this position, there is in fact no way that you can go ahead and get that carbocation at this position. Right? If we push the electrons this way, we're going to get a carbocation there. If we continue to push them, we're going to get a carbocation there. So you notice that it's sort of, as you're sort of pushing the electrons around, you continue to skip carbon atoms each way. And so what ends up happening is that this doesn't form at all, or it's not going to form. It's not going to be as likely to form as the others, in part because the relative stability of this one and this one are going to be sort of favorable. Okay, so if you were to run this reaction, again, we're not necessarily going to discuss specifics of ratios that you might get, but you could imagine that you could run this reaction and you'd expect to get some amount of ortho and some amount of para. And based upon other factors, right, if this methyl group was really, really, really big and the R group was really, really, really big, right, you might imagine, oh, well, based upon sterics, it's probably not going to go at that position. Maybe I'll get solely substitution over here. By the same effect, if it was something sort of smaller, you might imagine that based upon proximity, right, maybe you would go to this position based upon proximity on a smaller molecule, if they're sort of smaller. In addition, you have two positions here and only one position here, so you might expect a statistical ratio of 2 to 1. But we're not going to get into the details of that prediction. What I want you guys to sort of recognize, most importantly, is when groups are able to direct substitution in a specific position, and what types of groups will do this. And so you should often look at the sort of resonance forms. Okay? So this was one where we had methoxy. Methoxys are really, really good donors. They're very, very activating. Oftentimes when you have a methoxy in a group, the reaction can be done much, much quicker. But even alkyl groups will serve as donors as well. And so if we had a group that looked something like this, where this is a methyl group, and went ahead and changed all of these compounds, now we're not going to have that resonance. But what you'll sort of notice based upon the drawings that I've done here, right, is if you look at the same system, the methyl group will also donate orthopara as well. And what is the reason behind this? The other case is pretty obvious, right, because that oxygen has resonance donation, right? But what's special about this resonance form and, say, for example, the other resonance form that this one doesn't have? Yeah. Yeah, so in both cases, we don't necessarily have that resonance donation of the oxygen lone pairs. What we do have, as was just said, is that we do have tertiary carbocations. So in each case, we're able to draw a resonance form where we inevitably have that sort of tertiary carbocation. And so I think the point that I want to make here for sort of donors is that oftentimes it's very much the case that if you have a donor, and what we're generally talking about is alkyl groups, right? We're talking about certainly heteroatoms where there's lone pairs that can donate in. If you sort of look at the resonance forms, again, we've sort of discussed throughout the last, pretty much all of organic chemistry, we've emphasized the importance of resonance contributions and sort of recognizing factors that you've learned that are stabilizing factors. And so, again, we've seen tertiary carbocations as something that's favorable, and so that would be something that we'd like. So again, in the case of a methyl group, that's going to be orthopara. In the case of a methoxy, that's going to be orthopara. Really most heteroatoms, so if I just said, like, say for example, if it's sulfur, as you might imagine, that's going to be orthopara. If it's a nitrogen of some type, that's going to be orthopara. So all these cases where you have the ability to stabilize the resonance forms. So that's really important that you guys are able to do, is sort of draw these resonance forms, understand why they are what they are. And so these are sort of these cases. All right, so what if instead of having a donor group, we swap that out and put instead an electron withdrawing group? And question sort of becomes, yeah.
If it was an extremely bulky alkyl group, like a terbutyl, for example, would it be tougher to eliminate, to re-aromatize?
Well, you can always do the resonance form and and
okay.
right. So you could always do like the resonance form. But again, I think the point that you're bringing up is that if you have a steric limitation here, it might just form the para position or something like that. So there's little other things that you guys could probably rationalize and argue within the two. And again, you see right away, right? There's two positions for ortho where there's only one position for para. So if all things were equal, you'd probably expect to get a 2-to-1 ratio just based upon statistics. But again, sterics comes into play and everything else like that. So you know, if I were to give you a question and you know, if I were to sort of give a question like this, and usually what I would look for is just to know that it's orthopara. But if I were to take it to the next level and say, oh, here's an example where it only went para, give a reason why you might think this would be the case. Or here's a case where it went ortho. Give a reason why you might think that this would be the case, or something like that. Okay? All right, so in addition to donors, so these are generally molecules that we would think about as donors. We have to sort of consider the possibility of instead having sort of electron withdrawing groups, electron acceptors. And so certainly one that we've seen a lot is something like a ketone, right? And so what we want to do in this case is, again, just do the same thing. You sort of look at the possibilities and you think about the different resonance forms that can take place, and you start to consider what impacts these might have on the systems. And again, we're basically looking at the same molecule, so I can simply just redraw the group. The difference is now that I have an electron withdrawing group, right, at this position, I have a ketone, which now has the ability to pull away electron withdrawing groups. So in the case of the ketone, right, you may look at this position. We've had this come up in the past, right? We had this come up with, for example, additions into alpha-beta unsaturated ketones, right? And we said, well, where's the delta positive in this system, for example? And somebody brought up the alpha position because it was secondary versus primary, but in general, the sort of resonance, as we discussed, overrides this. And so here's another example of that as well. We do have this now tertiary carbocation. And so if you were to look at this and you were to still predict that this would go orthopara, you know, that wouldn't be the worst mistake in the world. That would make sense. You would at least say it based upon things that you knew. However, it turns out that it's the other way around. This, in fact, does lead to meta-direction, and it's for the same reasons we discussed previously. When you have something like a ketone, you have a sort of a polarized bond there, right, which leads to a delta positive or partial positive charge at the carbon adjacent to the carbocations. And so as we've seen throughout sort of class, right, especially throughout the conjugated systems that we've seen when we're trying to predict, for example, regioselectivity of these systems, usually what you want is a sort of a system where you have this delta minus, delta plus, delta minus, delta plus. So you have this flow going in between the two. That's in part because you never want to have sort of, or you want to avoid two positive charges next to one another. And that's what we have here in this case. By virtue of the resonance form, we also have it here, okay? And so the one molecule in this case that in fact leads to a system where you don't have that positive charge or those positive charges next to one another ends up being the meta position here. And so by virtue of the nature, based upon the fact that you cannot, in the previous we wanted to put the positive charge here. In this case, if we can draw a resonance form that has the positive charge there, it's just overall bad because of that. And so the meta-directing group is actually, in this case, what's going to drive this reaction. And so if you have, say, for example, a ketone, then that's going to give that effect. Now, it's important, again, I think within, you know, you guys sort of, you know, there's often interpretation issues. What I think is important to recognize here is that this is a ketone. We're talking about a ketone that's directly attached, right? So you have to really draw it out and look at the charges. If I had a, say, for example, a methylene spacer, so a CH2 in between there, not necessarily going to have those positive charges directly next to it. So it's important to consider that. Another place where people will often get confused is if it's, say, for example, an acyl group, right, where the oxygen where it's actually an ester, where the oxygen is the one that's bound to the group. And this is a case where, based upon resonance donations, this is still going to be orthopara. So again, it's the difference between it being attached on this carbon or being attached, for example, on the other side onto a heteroatom. So that's just important to recognize, draw it out, see those differences. And so you could probably start to predict other groups that would also be meta-directors, right? When you think about things like, if this is a sulfoxide or a sulfone, right? If that's an SO2pH or SO2R, right? That's another instance where you're going to have those groups there. Nitros, for example, you're also going to have a really good positive charge at that position. So again, anything that you might draw that might have a partial positive charge there. And so just some examples. Right? And because we've sort of learned to make these molecules, we should probably put the three that we've made sort of up here, right? So we learned how to do Friedel-Crafts acylation. So if you're doing a series of functionalizations on these, right? Certainly that sulfone, right, is going to exist at that position, or if it's the sulfonic acid. And again, nitro groups. Nitro groups are really, really electron withdrawing, in part because you've actually got a full-blown positive charge right there as well. So nitro groups are some of the most electron withdrawing substituents that we can actually have. Okay. So, as you might imagine, in this chemistry that we sort of outlined here, we really discussed it in the context of donors and where the positions would sort of go in. And I'm going to come back to the one that we haven't discussed yet, which is halogens. But I just want to make one quick point here. Say EWG for electron withdrawing groups. And it's something I don't emphasize and stress too much, but it'll become important in a minute, and I'll put it in the context where it is important. But as you can imagine, when you have electron withdrawing groups, right, in all these cases, it's what we call electrophilic aromatic substitution, right? We're treating the aromatic group with an electrophile, which means that our benzene, right, is a good nucleophile in these cases, or it's serving as a nucleophile. And so things that could then make benzene a better nucleophile will accelerate the rate of the reaction. And things that would do the opposite, right, things that would make it a weaker nucleophile would have the opposite effect. And so as you can imagine, what would be the effect of having a donor group on the benzene? Is that going to make it a better nucleophile, or is it going to make it a weaker nucleophile? If you have a donor, it's going to make it a better nucleophile, right? You're increasing the electron density there. You're stabilizing these carbocations that are building up. So for all these reasons, they're becoming better nucleophiles. And so certainly there's a lot of chemistry that's out there where once you start putting a lot of donor groups out there, maybe the chemistry will take place a lot quicker. You can do chemistry at lower temperatures, in these sorts of things, right? On the opposite side, though, if you have an electron withdrawing group, right, it can have the opposite effect, right? So if you have an electron withdrawing group, you're going to be pulling electrons away from that system, right? And so for those reasons, the reaction is going to be slower, right? Looking at these resonance forms, right? Again, we sort of described why this sort of ortho and para, you wouldn't want to make these because it has the positive charge there, but even in this case, right, inductively, that's withdrawing electrons from that system, so it's not like it's stabilizing this positive charge here. And so from the standpoint of electron withdrawing groups, that's really going to slow down reactions considerably. And in fact, if you read through the book carefully or you look through, problems and other books or whatnot, they'll often provide examples where, say for example, you have a nitro group on there and suddenly it won't do certain chemistry. And I'm not going to go that far into this. I don't want you guys, and part of it is just sort of my philosophy of sort of course, I think it's important that you know that you could do these. I think the ortho-para meta-directing is important. But if you, say, for example, show bromination on a dinitrobenzene, I think that's fine, even if it wouldn't actually happen in principle, in part because physically the ability to see that happen and imagine it means that even if the books conditions wouldn't work, you could probably find conditions that would work for you. So that's sort of why I don't worry too much about that. So on synthesis problems or whatever, don't necessarily worry about relative reactivity, although I could certainly ask you a question within that context where I said, here's one that doesn't work, and here's one that does work, and explain why, right? But that should be fairly easy, right? If you've sort of listened to the class, you should sort of recognize that, again, if it's through electrophilic aromatic substitution, it's going to react slower. Why? Because you've effectively made the benzene a weaker nucleophile. But again, I wouldn't expect you guys to predict whether something's going to be reactive or not. It would be more like a mechanism, like an exploratory or explanation-based pathway. So in general, donors end up being orthopara directors. Electron withdrawing groups end up being meta-directors. If you're sort of paying attention, you're thinking about all the different groups that we were able to put on here. You might sort of recognize the one that I left out, and that's halogens. Okay, halogens are inherently electron withdrawing, right, in nature. They're, they're sort of very electronegative. We sort of generally think of them as accepting electrons, say, for example, as parts of electrophiles. And within electrophilic aromatic substitution, certainly halogens on aromatic groups make the aromatic group inherently more electron positive, if you will. So they will, if you could sort of look at the electronics, they'll sort of make it a weaker nucleophile, right, by having halogens on there. But in terms of the directing effect, and I'll just put X, these are a little bit different than the other electron withdrawing groups. For a reason that I would gather you guys would probably be able to predict, right? So what is the difference between a halogen and, say, for example, the acyl group, or for example, the sulfone or the sulfoxide or sodium nitro? Yeah. We got the lone pairs, right? We got the lone pairs directly next to it that we didn't have in those other cases. So that's the one thing that's going to fundamentally make these different. In the other case, you had a carbonyl there, so you had this delta positive. But in this case, what you do have is you have the ability to donate back with lone pairs, giving it resonance stabilization. And so again, the overall system, it still makes it a weaker nucleophile. But given all the options, this one versus this one over this one, when you think about the relative energies between those three different structures, halogens on aromatic groups actually leads them to be orthopara. So say X, halogen, bromine, iodide, fluorine. I don't know about fluorine, but we'll just stick there. You say equals orthopara. I bet fluorine would as well. I'm not used to thinking about fluorine on aromatic groups that much. But since we haven't really done anything with fluorine, we don't have to worry about it too much at this point. But at least the ones that we generally deal with, bromine, iodide, chlorine, these are the ones that we see the most. And these are the ones that we've seen methods to do substitution on. Those will all direct electrophilic aromatic substitution to the ortho and para direction. So does this make sense? So again, this is where drawing resonance forms is important. You're drawing upon concepts that you guys have seen in the past in terms of stabilizing factors of carbocations, whether it's resonance stabilization, whether it's more substitution in a position to make it stabilize, or on the reverse, if you're in a situation where you need to have, some, say, for example, some type of withdrawing group. Right, so where is this kind of stuff going to be important? Well, certainly if you get a reaction on the exam and you say, what is the product from this? That might be one place, so you should certainly know and recognize what these are going to direct. But the other place where it can come up and can be pretty important is, say, for example, in synthesis. Specifically, one of the things that when we're doing synthesis problems, once we get to aromatic chemistry and benzene substitution, let's say, for example, you want to put multiple groups on the benzene, sometimes it'll often become important which order right, you put these groups in, right? Because, say for example, if one group is a donor and one group is a withdrawing group, well, if you want them meta, that might be in one direction, but if you want them para or ortho to one another, then you'd probably swap those. So let's do a quick little synthesis problem to sort of explain this. And again, I'm not going to worry about whether a reaction might work or might not work. All that I'm concerned about for your guys' sake is, are we going to, where would these groups go if it were to proceed, okay? So this is a synthesis problem. And let's say, for example, we want to make para-nitrotoluene. Okay, so we've got benzene, we want to make para-nitrotoluene. Okay. We have to put a methyl group on, and we have to put a nitro group on. But we have to pay attention to which one may need to go on first, so that the chemistry can actually take place. So the first question behind this is, well, how might we physically put those groups on there? What are the conditions that we would need to substitute in and put, for example, on a methyl group? And what are the conditions that we would need to put on a nitro group? So to put on a methyl group, what are the conditions that we would need for a methyl group? Say it again? Heard something? I can't. I'm hearing mumbles.
Instead of electrophilic carbons.
An electrophilic source of carbon, right? So you're going to need an electrophilic source of carbon, but what is the electrophilic source of carbon that we generally put on there? So what is, if we want a methyl group, what's our electrophilic methyl group? Maybe iodomethane or bromomethane or something like that, right? So we have that electrophilic source, but is this going to be good enough to react? No, so what do we have to add to it? Yeah, something like iron tribromide or something like that. Right? So, or aluminum trichloride, or again, at this point I don't really care which one you choose, it's just important that you recognize that you need a Lewis acid. And so that's kind of the point that I want to bring home, is that this isn't quite a good enough electrophile, so you have to add something. If you choose aluminum trichloride or whatever, I don't really care. I just want to see that you add the right, that you have that component that is electron withdrawing group. And you're absolutely right. And this would be a sort of a Friedel-Crafts alkylation, right? Not an acylation, an alkylation. All right. So that's how we're going to put a methyl group on there. If we wanted to put a nitro group on here, sort of refresh our chemistry, how do we put nitro groups onto these compounds? Nitric acid and sulfuric acid, right. So HNO3 and H2SO4 will give you the nitro group. Okay. So this is how we put those groups on there. Again, that's the first part that you guys have to remember. But now if we want to do two of these back to back, we have to sort of consider which order we want to do these in. So are we going to put the methyl group on there and then do the nitro addition, or are we going to put the nitro group on there and do the methyl addition? Okay? So you guys are already getting ahead of me. So with the methyl group, if we were to go ahead and take this molecule and treat it to these conditions, where would the nitro end up? This is a donor. This is a donor. So it would be ortho or para, right? And so since we want para, that would work. Again, we'll get a little bit of ortho, but we're not learning too much about selectivity of ortho versus para at this point. But yeah, if we were to take this molecule and treat it to nitromethane, or sorry, excuse me, not nitromethane, if we were to treat it to nitric acid, and sulfuric acid, we get a little bit of that. We'd also get the ortho as well, but the synthesis problem, we want to know that at least we would get a reasonable amount of that. Now in the nitro group, if we went ahead and used these conditions, where's that methyl group going to end up? It's going to end up meta, right? So the nitro group is a meta director, right? So in this case, what we would do is right, is that we would get to right, that group there. So if I gave you guys a synthesis problem, right, and let's say, for example, this is a 5-point problem, synthesis problem, and I basically asked you, make this molecule from benzene, right, this would be the answer that you would want, right? If you did this answer, maybe you'll get a 2 out of 5, depending on how generous I am, maybe 3 out of 5, right? And so, again, it's important that you know the reactions, but then taking it to the next level, it's important that you recognize this level of selectivity as well, right? So that's kind of what I want you guys to do in terms of synthesis. All right, so this was a fairly straightforward example because there's only one group, and then we were playing in a second group. The question next becomes, what if we're in a situation where we have 2 groups on there, but the location of those 2 groups are sort of at odds with one another, where if you looked at one group, that might put you at one position on the ring, but if you looked at the other group, it would put you at the other position. So let's discuss an example like that. Actually, I just had a good example like that. Let's do this. All right, so let's say that we had this meta nitro toluene, okay? And we wanted to take this and treat this with, I don't know, let's just say set electrophile, just to sort of keep it sort of more general. In this case, we now have, unlike in the previous case, we now have really 4 positions, right? Previously we kind of had 3, but now we kind of have 4. That we may have to consider, in part because we've desymmetrized the molecule. Okay, and so let's go ahead and draw those possibilities. So try to copy and paste button. Okay, so if the electrophile can end up here, I'm just going to sort of around. Right? So here we have a position that is, in essence, so in terms of the methyl group, it's going to be ortho to that one, right? And in terms of the nitro group, it's also going to be ortho, okay? In this case, we have methyl group being para. In this case, we have the nitro group, what relative to the nitro group, we have it being also ortho, okay? In this case, we have relationship to the methyl group, we have it being meta. Right, and in relationship to the nitro group, we also have it meta, right? And in this case, related to the methyl group, we have it ortho, and related to the nitro group, we have it para. Okay. So we know that in this case, we're going to sort of look at this, and as we sort of go through all the possibilities, what we'll notice is that really none of them match what we want. So methyl group is certainly an ortho donor, right? But a nitro group is a meta donor, right? So it matches here, but not so much there. In this case, again, methyl group is certainly going to be a para donor, but it's not going to be sort of ortho donor. In this case, the methyl group is going to be a meta donor. That's bad, right? But in this case, the nitro group would be a meta donor, so this would be good. Right? And in this case, we have ortho, and the para is not going to sort of work. And so what we're looking at here is this situation where, based upon the fact that we put it meta on the system, there's really only one structure in here that the nitro would tell us would be good, right? There's only one position here that's meta because the other meta position is sort of taken up. But then we also have these 3 additional positions that would be good for the methyl group. Okay? In general, when you come across sort of a problem like this, it's good to sort of look at the molecules just like we have. And the first sort of rule that you can sort of imagine, and this is the one that works, okay, is that usually the donor trumps, okay? And you can think about that in terms of really good resonance stabilization, for example. The fact that it's serving as a nucleophile, right? So the group that is making it a better nucleophile might be the position that sort of trumps it. So right off the bat, what we could say is that this structure here, where it's meta, that's probably not going to sort of happen, right? Because the methyl group trumps. If the methyl group trumps the nitro group, then in this case, that's not going to be the case. It's going to want to direct to one of the others. So now we're in a situation where we basically have 3 structures, and truthfully, I think it's going to be very difficult to predict which one of these would be the case. So if there was, say for example, an exam question that were like this, I would expect you to probably write all 3 of these as possibilities, because they all should be possibilities. But if we want to take it to the next level and just sort of think about it a little bit, could you guys reason how maybe one of these wouldn't likely take place? Is there one that looks like maybe it's just not going to be that great? Yeah.
The one next to the NO2,
So it's next to the NO2 in 2 places. It's next to it here, or next to it here.
Where it's parallel
This one here. So you're thinking that the nitro, that the electrophile next to the nitro might not be as good, in part because it's an electron withdrawing group, and that's where it's going to have the greatest inductive withdrawing effect. I think that's fantastic. So I would agree the same, but that's going to be the case here and here, right? That's going to be the same case in both of these. Okay. So it would be bad for both of those, which would ultimately get you here. And if you were to say, okay, I think I'm going to get this one, and this is the reason why, I would basically believe you and say, great. The other thing is that you have this one position here, which is oftentimes a pretty bad position as well. Why might this be just a bad position overall? Sterics, right? It's sort of in between the 2 groups. So from a steric standpoint, I would say this is probably the least that you're going to get, right? For the reasons that was just brought up, I would probably guess that this one is probably, you might get a little bit of this, but less of this than you would of this. But yeah, you're probably right that this position here would probably be the one that you would get the most out of. And so, again, from an exam standpoint, I think all 3 of those would be fine. If you were going to rule out one right away, I think that this one would probably be the easiest to rule out from a steric standpoint, and that sort of might make sense. But again, I would say, sort of, if it comes up, to play it safe, you can list all of them. If you're going to list the one that you think is the best, maybe explain why you think that one might be the best. But again, I think sort of going through this exercise and recognizing that the donor is the best is the way that you should sort of go at this. And this is going to be the same, another example where this might come into play, right, would be a case where we have a donor that's a halogen, right? In that case, say for example, we have a bromide at that position, right? Now we've got a system where we have another 4, but again, which one would sort of dictate the selectivity? It's going to be the methyl group, right? Not the bromide. It's going to likely be the methyl group. So. All right, so that's just sort of electrophilic aromatic substitution. All right, so I'm going to make one quick announcement, and then we'll move on to the last part of this chapter. And that's that. This is the last course. This is the last class before the break. right? So now you guys have a couple weeks. The first day that when we come back, assuming that I didn't screw up the schedule, you do have a class on that Monday, I believe. That Monday will be a review, so that'll be a time to sort of get our bearings together, and then the next day that we come back, that will be the exam. Yeah. There was confusion. I think I accidentally left. I forgot to switch the M with the W. So whatever the date is, that's right. So I think I just made a typo and just left M where it should have said W. So basically, we come back. It's a Monday. I forget exactly what the day is, but we come back and we have class on a Monday. That'll be a review, and then Wednesday we'll come back and we'll have the exam. Okay. So, and after the exam, there's really only about 5 classes left after that. And so what we'll do with those remaining 5 days is we'll have 4 classes where we'll try to get through amines, carbon-carbon bond forming reactions, probably a little bit about polymers. If we can get into a little bit of biology type stuff, I will, but it'll be sort of just a sort of a survey type class, and then we'll have a final exam review class. Okay, so that's just so you know what's going on. So everything through this class is going to be on the next exam. Really what we've covered, if you sort of just review, is diene chemistry, right? So Diels-Alder, Claisen, nucleophilic attack, for example, of dienes, and then all this stuff with an aromaticity. So that's really going to be the focus of the next exam. All right, so what we've been focusing on for the last bit of this class has been electrophilic aromatic substitution, right? Where our aromatic groups have served as nucleophiles to react with other compounds. And so there's a parallel that we can draw here between a few different types of reactions. So again, if you take the alkene and you treat it with, say, for example, bromine, right? If we take this and we treat it with bromine, right? In this case, what's happening is the alkene is serving as the nucleophile. And this is going to be the electrophile, right? So think about ammonium. Just in terms of that first step, right? So we've seen alkenes serve as nucleophiles, and then we suddenly came back and saw instances where alkenes could also be electrophiles, right? And we saw this within Michael additions. But if you sort of recall, in general, the compounds that we really focused on were molecules whereby there was some type of withdrawing group on that alkyl group. And what I mean is a resonance withdrawing group. We're not talking about a halogen, for example. What we're talking about is like a ketone or a nitro or something of that sort. Certainly, something like methyl vinyl ketone is a fairly straightforward standard one. We discussed it like acrolein and stuff. Right, and in essence, we've seen examples where now right after sort of polymerization and so forth, we effectively get beta substitution, right, of these alkenes. And so there has been versatility that we've seen with alkenes, that there's this nature to them where you can use those electrons and use them to attack things, or you can push electrons towards it, have it serve as an electrophile, and have the electrons go in the other direction, as indicated here. And given as how we're sort of trying to sort of view a lot of this stuff as extensions of alkenes, except in conjugated pi systems, you might imagine the same type of dichotomy is at play with benzene as well. So there's not a ton to nucleophilic aromatic substitution. Um, but again, it's an important reaction and one that we'll certainly go over. So some of the standard nucleophilic aromatic substitution that we have can be based upon this sort of idea of looking at those enoic systems or withdrawing groups within the alkene system. So say, for example, that alkene had, say, the methyl group on there. You can now see that built within this system, right, is a is that sort of enoate. And so the first part of electrophilic aromatic substitution is going to involve sort of recognizing groups like this, where by virtue of the fact you have a group on there, you can sort of add in essence, sort of 1,4 or sometimes even 1,6 into these systems. So that's the first part. But the other part that you sort of have to keep in mind here is that, again, this is sort of nucleophilic aromatic substitution, right? And so you're actually doing a substitution in this case. And the substitution that you're doing this with is something that you've, in general, seen quite a bit. It's our general leaving group, which is a halogen. So usually what you'll have is a group at that beta position that's, say, for example, a bromine or a chlorine or something like that. So you know, when you're doing nucleophilic aromatic substitution, you're going to start to identify things that look something of this sort of sort. And when you have a molecule like this, and you're just thinking about standard nucleophilic aromatic substitution, you could actually begin to add really, in many ways, whatever the heck you want, right? There are lots of different nucleophiles you can imagine. Add in here, oftentimes it's described in these systems as amines, for example, but you can imagine if you took this molecule and treated it with, say, for example, methoxide, sort of predict what's going to happen here, right? And that's that you have this enoate, you've got this bromine here, and what can happen is the MEO can attack, right? And when we attack at that position, and this is what's important, is that we can attack in part because now we can take those electrons and push them up onto the oxygen. Okay? So why can we not right? So we'll be at something like this. So why can we not just attack and have the bromine leave? Right? We can't do that in part because you can't do standard substitution chemistry, right, on an sp2 hybridized carbon. But this, in many ways, is kind of like an extended acid chloride, or in this case, acid bromide, right? So you've seen additions into acid chlorides, right? Remember, acid chlorides are something like this, right? Except that now it's just in conjugation with the alkene. So it's the same type of addition that we would see into an acid chloride. But now what happens is when we get to this intermediate here, there wants to be a drive to reform aromaticity. And when you kick back down, right, you have a couple options that you can eliminate. If you eliminate the methoxy, you're just going to go in the reverse direction. But if you eliminate the bromide, then you generate a new compound. And you effectively get your substitution. Okay? And so this is an example of nucleophilic aromatic substitution. Again, the sort of nucleophile coming, you're treating this with a nucleophile. Okay? So what you notice, which is kind of important, there is a direction that's sort of necessary here, a relationship between the electron withdrawing group in terms of the electron accepting group, I should say, and ultimately the leaving group. And that's that, and we'll see that the relationship between the two, these need to be in order for this to work, they need to be either meta to one another, sorry, ortho to one another, or they need to be para to one another. And so in this case, you'll notice that this molecule is in fact ortho. Yeah.
Wait, so what contribution does the zero chloride have for the leaving of bromide again?
Say that again?
So what contribution does the zero chloride have then? For bromide leaving the benzene?
Why would the bromine leave
Yeah, like
rather than methoxy?
yeah.
Well, bromine just stabilizes the negative
No,
charge.
I mean like you said you add like a zero chloride.
So to attack this alkene, for this alkene to behave as an electrophile, that's why you want to draw the parallel to what we saw earlier with like Michael additions, adding into alpha-beta unsaturated ketones, for example, where then the alkene becomes an electrophile. So the important point here is that you can attack this carbon in part because you can push those electrons up into the system. So we'll get to more harsh electrophilic aromatic substitution in a minute, but I always like bringing this one up. So this is sort of one example. So this would be substitution that would work at the sort of so when these two are ortho to one another. It can also work if they're para to one another as well. Okay, so if that group is para, you've just extended the pi system two more carbons. Okay, but as you push the electrons, what you'll see is that we can also push the electrons up onto that ketone as well. Everybody see that? So through that additional pi system, right, in conjugation with everything else, you can do the substitution of para. So you need this sort of electron withdrawing, you need the leaving group, the one that's going to get substituted, and whatever the withdrawing group is. Again, we're showing it as a ketone here. You can imagine it as an ester, you can imagine it as a nitro, you can imagine it as a sulfonyl. But they need to be ortho or para to one another. Why can they not be meta? Well, let's take a look at meta really quickly and sort of ask ourselves that question. And effectively what it comes down to is that there is no way that you can attack at that position, at the meta position, and have those electrons go through into the carbonyl, right? So this is very similar to what we saw in terms of things can be ortho and para directing, but they won't be meta. It's almost like they always skip a bond, right? So there's this sort of pattern that you see. Right? In this case, we can't attack there because, in essence, the resonance form, which is basically a negative charge there, right? In this case, which can donate there, that negative charge can be there, it can be there, it can be there, it can be there, it can be there. Where it can't be is there and there. Wait, yeah. So it can be there, it can be, can't be here, or, sorry, it attacks here, the negative charge can be here, here, or here, it can't be here, or here. In this case, you can put the negative charge here, here, or here. So you can put it here, here, or here. But you can't put it at this carbon here. Right? And that would be the carbon that you would ultimately stabilize those electrons. So if you go ahead and you try to push electrons through that system, what you'll notice is that you'll only be able to put that lone pair at these three positions. Okay? So you can go ahead and try that on your own. But again, this is something that's sort of important. It also comes up that if you want to have a system of selectivity, right? If, say, for example, you have a molecule that has two halogens on it, there can actually be selectivity here because of that, right? So if you had a system where you had two halogens, you can sort of take advantage of this. Because if I were to take that molecule and treat it with, say, for example, methoxide, right, only one of those bromides is going to swap out, right? So you can actually have some selectivity here. Is it going to react in this one or this one? First one. It's going to react on the top one. So you can actually get selectivity based upon this. Okay, so this is the sort of standard for general nucleophilic aromatic substitution when you have a leaving group on it. So again, take this and run with it. You know, you can be creative. Have these systems, as long as you have a withdrawing group that can stabilize resonance and a leaving group, you can sort of imagine doing this with really any Euclid file that you might want. Okay. Now, obviously, there's another way that you could do this, and maybe in a synthesis problem, for example, that would be a lot safer. Right? What would that be? If I want to take an aryl halogen and say, for example, if it's a heteroatom, then we have those deals. But let's say, for example, we want to put a methyl group at that position. We're probably not going to use methyl Grignard, right? You probably just use a cuprate, right? So you use a cuprate again, and that would just be your standard, Gilman type substitution chemistry. So again, in a Gilman, you wouldn't necessarily get the selectivity that we just outlined there. So there are some limitations to it. Okay, so this is one class, and probably the more practical class of oxidoprylium cycloaddition. Or sorry, excuse me. Having a Freudian slip of my research. Of nucleophilic substitution. It turns out that you can, though, in fact, substitute chlorides, like, say, for example, just an aromatic group with a halogen on it. You can actually begin to do chemistry on this. You okay?
Yeah.
So if we say, for example, treated this with sodium hydroxide, you can, in fact, induce chemistry on this. You can, in fact, do substitution. But if I were to take these two and react them together, nothing would happen. What you need is a ridiculous amount of heat and pressure. So under extreme conditions, of extreme heat and extreme pressure, you can get this to go. That's some specifics. I'll just say high heat and pressure. Okay, you can actually get this to go, but it goes through a completely different mechanism than you might imagine. It's not your standard substitution reaction where the OH goes and, in fact, eliminates. In fact, it's something that might look even more bizarre to you guys. And that's that it goes through what's called benzyne. So what can happen under these high temperature systems, this is the first step, is you actually do sort of a syn elimination. Okay? And you get a molecule that I would never ever want you guys to draw. Because of the fact that, as you might imagine, it's highly, highly unstable. So that's a molecule called benzyne. Okay? Very, very, very highly reactive. In fact, it might not even exist as I've drawn it. Why would that be really bad to draw? Yeah. Yeah, because it's SP and it's sort of six-member ring. What kind of geometry does SP want to have? 180, right? So these bonds want to be 180, but you've sort of pulled them to one another. And so oftentimes it's sort of questionable what the actual structure is, but sometimes they'll even say that it's something like somewhere between these two to separate the charges. I actually had an interesting story. Let's see if I have it drawn down. I didn't draw it down. When I was in benzyne can be really, really useful in chemistry. It can sometimes be difficult to control, but there are certainly people that are working on it that are sort of understanding chemoselectivity of these processes. There's actually a really young chemist named Neil Gark who's spending a lot of time currently, so he's just sort of, he's a little bit into his career, he's a few years beyond me, but it is really making some nice contributions, which just shows you how important it still remains and what a challenge it still remains to sort of get selectivity in these systems. But at least in terms of the standard benzyne and using benzyne as reagents, just benzyne rather than functionalized benzyne. When I was a postdoc at Yale, my first semester there, we were trying to make some benzene precursors. And these molecules are extremely, as you can imagine, high in energy, and so the moment that you generate them, they're very, very reactive. And I was making these precursors to them, which, within their own right, I think it was something like this, I forget the exact structure. Something like this, or as a precursor to that I was making, right? And when you look at a molecule like this, show the other resonance form. This is a common precursor to benzene, and why would that be? What do you think you could do really easily with this? You could do a decarboxylation, and then what? Lose nitrogen gas. And so when things explode, right, when there's explosions, what's generally happening in an explosion, right? You're usually going from solid to a gas, right? So the volume just increases really, really, really quickly. So if you look at like TNT, for example, what's generally happening is you're generating a lot of nitrogen-based gases within that sort of system, and so the volume just expands really, really quickly. So when you look at this, right, you're basically going from a solid, and each, gram of that solid, right? Say, for example, you have a gram of that solid, almost probably half the mass. I don't want to do the math off the top of my head, but a very high percentage of the mass is suddenly going to become a gas. And so, think about the volume of a gram of solid, and then think about the volume of a gram of gas. The difference in volume. So as I was working with this, I was very scared. We always had these blast shields up, and I had like heavy-duty gloves on, and I'm sweating profusely as I'm sort of working with it. I got all done. The chemistry didn't work, but that's for another day. But I was cleaning up, and just a little tiny speck of this was on my, I guess it had fallen. It was like in my hood, and I didn't know what it was. And so it's very shock sensitive, and I went and just like scratched it just a little bit. It was tiny. It scared the hell out of me. It was like a pop, like really loud pop. So it wasn't as dramatic as I thought, but it almost sounded like those little popper guys you would throw. So that was what happened. Anyways, that's just a side story. Not as dramatic. You guys probably thought I was going to talk about losing a fume hood, but it wasn't. But anyways, this is usually how people like make benzene, is through intermediates like this, and then they make it in situ and react it. But this is how we would do it here in this kind of setting, again, at a very high pressure. This is something you can do at room temperature. But what happens when you get to something like this, right, is now you've got your water that you've just generated. And so you might imagine, right, that depending on how you want, actually I think it's electronic force, so it would react first. Forget the exact order, but I think the water, this is going to be higher energy than this. So I think the water first attacks here. And then when you want to draw intramolecular, like it's sort of reaction. So basically what happens is you generate a benzene, which then this effectively serves as the electrophile for this system. So it's not, it's not like what we saw previously of just something attacking and sort of moving electrons around. It's a little bit higher in energy. If you go with stronger bases, sometimes you can promote this with like diisopropyl amide. For example, you can sometimes promote this type of chemistry as well, but it's not really all that useful because of some practical aspects to it. But there are other ways to go about making benzene, and so it's sort of worthwhile seeing this. And again, there is work that's currently being done that's trying to really make this type of chemistry much more useful. But this usually people don't consider benzene as reagents too much in their strategy. Okay, so that's in terms of nucleophilic aromatic substitution. We're not going to get into regioselectivity of benzene and stuff like that. Although you might imagine looking at some of the resonance forms and thinking about benzene and thinking about which resonance form of the two might exist a little bit stronger, so you can consider that. But benzyne's just sort of more interesting than anything. All right, so we've got about 10 minutes left, and we're basically through. So we're basically through. That's really all that I wanted to cover for aromatic chemistry. I did realize that I missed a couple things, so I'm just going to backtrack with my remaining 10 minutes here and just discuss a few things that I skipped over that are not crazy. They're just a couple reactions that we didn't mention. But there are reactions that I think that you guys could probably predict even now, but we'll just sort of show them now anyways. Okay. And one of them, and then I'll let you guys go really, unless you guys have questions. But going back to electrophilic aromatic substitution, we discussed how if you take a molecule and you treat it to an electrophilic sort of cationic R group, and so again, we discussed Friedel-Crafts acylation, we discussed Friedel-Crafts alkylation. We often discussed ways that we could make full-blown carbocations in other ways, right? And so one of the things that we discussed was that if you take this molecule and treat it with, say, for example, a carbocation of this nature, which could in principle be made through, say, for example, it's propylene and some type of acidic source, right? We can begin to get to substitution chemistry sort of that type. And I kind of sort of asked you guys how you guys might know about making cations, and this was kind of the one that came up. It happened to just be the one that was on my mind, and maybe somebody even sort of said it. But what other early reactions, in fact, one that I think we discussed towards the very beginning of this semester, did we also generate cationic intermediates? What's that? Yeah, sort of, well, SN1 in essence, but specifically there was a reaction that we learned at the beginning of this semester from alcohols, right? So we can get there from alkenes, but we can also get there from alcohols, right? If you think about some of the chemistry that we've done, if we had, say, for example, terbutanol, and we treated this to HBr, right, what's going to happen in this reaction? We're going to propionate, right, the alcohol. We're going to leave sort of a carbocation, right, and then that's going to get trapped with the bromide. Generate that compound there, right? And so, again, the sort of point that I want to bring up, and the book does discuss this as well, is that if you have an alkene, you can sort of start there, but from the same intermediate, you can also get there from alcohols as well. And so from the same sort of concept, if you came with an alcohol and used an acid, you could generate these intermediates as well, and phosphoric acid is usually the one that's chosen. This is the one the book discusses, but the point is you guys sort of know is you need some type of acidic source, you propionate that, and then leave behind sort of cationic sort of intermediate. So this was one reaction that I sort of wanted to mention that I did earlier. You can sort of tell it's simply an extension of what we saw previously. You can generate a carbocationic intermediate and something that can react. The one other reaction we didn't really discuss, and maybe I'll spin this in a slightly different context. I'll sort of build off of this really quickly, because it's just one reaction. It's a pretty important reaction. But it is just one. And so we talked about phenols last class, and we talked about the relative acidity of these compounds and how they're fairly acidic, and so you can get away with things like potassium carbonate. things like potassium carbonate will be strong enough to in fact deprotonate. That's right. And what you have in this case is now we've been talking about nucleophilic aromatic substitution, having lithoxy up there, for example, but now, and that being a good donor, but now we have a charged donor. And so it turns out that once you deprotonate these species, what ends up happening is now it's an even better nucleophile. And it turns out that you can actually take these molecules and just treat them with carbon dioxide. And I think in part, at least due to sort of coordination chemistry involved, you actually get some direction to this based upon proximity. So previously we were just talking about, orthopara. In this case, it's pretty high selectivity. Excuse me. Excuse me. All right. But you get pretty high the workup. We get pretty clean conversion to that molecule there, and that's salicylic acid, right? Basically the precursor to aspirin and other things. So, so again, done on an industrial scale and so forth. But this kind of stuff can sometimes work for other electrophiles as well. So, again, I wasn't really planning on talking about this. And I won't spend too much time, but if you think about the direction, part of this could be due to the fact that in proximity, right, you're closer to where that negative charge is. So based upon proximity, it'll induce there. But you also have these possibilities for sort of the counter ions actually directing some of these groups. And so you could even do things like acyl direction to these positions as well if you wanted to, say, for example, trap that with an acyl chloride. Actually, I don't know about that. That might distort that position. So never mind. But anyways, this was just another reaction that we sort of saw. It should be an extension of what you guys have seen in the past. Carbon dioxide as a sort of an electrophile. So, so with that, I guess I'll let you guys go. Have a good break, and I will see most of you guys next Monday.